study, Phase Two. Maybe a number of you know about Phase One. Our team members are here to help answer questions. Doug Beyerlein, the author of the Western Washington Hydrology Model, Jenny Saltonstall, hydrogeologist, Bryan Berkompas doing the flow monitoring, and Ann Cline, our professional landscape architect on the project. Just a reminder, this work is NPDES funded through the Strategic Stormwater Action Monitoring group, and City of Olympia is gratefully our sponsor. Eric Christensen from City of Olympia is on today, and as always, ecology staff supported. Brandy Lubliner has been really great to work with. Thank you, Brandy. And just a reminder, please do ask questions during the presentation. I don't feel so rushed as in other agendas when we only have 20 minutes and 10 minutes for questions. So we have a little bit of leeway, but we do want to get through it all. The purpose of the Phase Two study is to assess facilities, bioretention facilities designed using the Western Washington Hydrology Model of 2012, which includes the bioretention module. And we went through a selection process and chose 10 built facilities to measure all of the dimensions and hydrologic conditions in those facilities and compare them to the model. In other words, how well do constructed bioretention facilities perform compared to their design models? And what conditions may be causing differences between actual performance and model performance? In the two phases, there were 10 sites each. In the first set, which by the way was sponsored by the City of Bellingham, those facilities were prior to the use of 2012, Western Washington Model 2012, and they're generally a bit older. And so they didn't have the benefit of the bioretention module that's in the current version of the Western Washington Hydrology Model. The second 10 were designed using that model. And they're, as a result of being more recently designed, obviously they were quite a bit younger as a group. Here's a distribution of the sites in this second set, all the way from 2 in Bellingham, 4 in Snohomish County, down into Renton, Tacoma, and outside Olympia in Thurston County. And by the way, that distribution was fairly similar in the first 10. So we have quite a wide range of both climatological and hydrogeologic conditions that we're working across. I'm going to go through a number of photographs just showing what some of these look like. This is Ann, our landscape architect. Hi, Ann. These are first few sites that we'll see are sites from the first 10. And so you can see that they're grown in a bit more. A lot of wide range and selection of plants and different mulching conditions. This site is one of the sites from our current set of 10. This is in Bellingham. One of the big differences in the second set of facilities is that a number of them, I believe it was 5, are actually retrofit projects. So they were fit into existing mostly roadway infrastructure, and this is an example of that. Oops.
That one looks horrible.
And my having a little trouble with the advance here. I'm not sure what is going on with my cursor. All right, here we go. So this is another of the current facilities recently constructed at a school. By the way, schools are a very big user of bioretention facilities. Both in the first 10 that we assessed and the second 10, there were quite a number of facilities fit into the grounds at new public schools. Oops, not sure how to better do this. Another one in Monroe. The previous one was, I believe, down outside Tacoma. This is in Monroe. This is also in north of Monroe in Snohomish County. We didn't actually select this one, but there's another one behind the building at the same site, and this photo just shows the construction process as they're being built. Here's a current one in Marysville. This one was interesting because in the background there behind the cyclone fencing is tidal water. And we were actually able to see fluctuations in the groundwater, but it did not affect the infiltration process. Here's a list of the performance monitoring components that we assessed in the field. Facility dimensions, bioretention soil and subsurface composition, and the hydrogeologist did infiltration tests. Measured the hydrology, the actual rainfall, inflow, outflow, ponding, and groundwater elevations, and the vegetation, herbaceous and shrub composition. We'll have a comment about that here in one of the other slides. Here's an example of the equipment that we're using, a rain gauge, of course, on the left, and compound flow weirs that allows us to measure very low flow rates in the V notch when the flows are low and still get a good signal on the stage, but also allows a higher flow through the rectangular weir when the flows are higher. So that was a very clever way to catch the full range of flows. So we analyzed all of these components for design improvements. And in the phase 2 site findings, what we found was that 3 of the facilities had smaller bioretention areas than reported, and 6 of the facilities had small ratio of bioretention area to drainage area. And the way that we are able to actually measure, the hydrogeologist, Jenny and her crew, were actually able to measure the bioretention area was during their infiltration tests. They did full flood tests, as in the picture here, to get their infiltration rates, but also filled it up to the elevation of the overflow. And in this case, I expect it's this elevation over here where this kind of nested cover on the overflow is. And when the elevation of the water gets to that point, they're able to measure the entire infiltration area that's active when the water gets to that elevation. So it's a real direct measure of that bioretention area. Here's a table of those dimensional findings. The main thing here is that in the data in red is that these are the TIR, Technical Information Report, areas reported. And these were the bioretention areas measured through that flood test that you just saw. So you can see the ones that are highlighted in red, the actual areas were considerably smaller than what was anticipated to be built in the TIR. by, in a couple cases, quite a lot. The other thing to notice in this range of our sites is that there were 5 retrofit facilities, and those retrofit facilities, recall, have a lot more leeway in their design under the stormwater manual. Essentially, they can be designed at the engineer's best professional judgment rather than meeting other design criteria that new and redeveloped facilities must meet. Then in this last column in yellow, this is the ratio of the bioretention area, again, that fully flooded area, to the contributing area. And you can see a number of them are quite small in yellow. And the reason these were highlighted is that they're less than the kind of guideline recommendation of 5%. And Doug is reminding me that that's just a really rule of thumb. And what we're really finding is that each of the facilities has such unique conditions that you start with that 5%, but have to make better judgments based on especially the subsurface native soil and infiltration conditions, and the relative amount of impervious area. So an area that is fully impervious, you're going to have quite a lot more water, obviously, than if your contributing area has some pervious area. Here are the findings from the hydrogeology and geotechnical investigations. Again, the sites covered a wide range of geotechnical and infiltration conditions. The bioretention soil texture was generally coarser than guidelines, both in phase 1 and in phase 2. There's a wide range of infiltration rates, and at times there was little specific hydrogeologic data, and sometimes borrowed information from other nearby excavations that were not exactly where the cell was going to be constructed. All right, come on. Here's how we got the soil media composition and subsurface geotechnical conditions, as well as install the subsurface well that monitored the groundwater. So Jenny's crew conducted this excavation. As they pull it out with the coring device, lay out the sample on a sheet of plastic, and they're able to send that to the lab and sample it, analyze the soil composition, and then take the subsurface well point and install it in the hole and put a stage recorder in the bottom of that. And that's how we had continuous record of the groundwater. This is a little bit of geotechnical detail, and maybe folks that know this area in the audience want to ask questions on this. Jenny's available, but there's a wide range of the conditions that the sites were located in. And this is the same as the first 10. This was one of the more interesting findings, at least to me, in the bioretention soil media composition. The dashed lines in here is the recommended grain size distribution from the Stormwater Management Manual. And these are the actual values. And by the way, this is from our phase 1 sites. And in this lower range of the distribution, this is in the fine sands and silts. And as Jenny has explained to our team, these fine sands and silts are what fill the voids in between the larger particles to help reduce the flow rate and has the really biggest effect on infiltration rate through the media. So if you have a lower proportion down in here, that means you have a larger potential voids between the media to pass, for the water to pass through. In the first set, the older set of facilities, it was pretty consistent that they were all outside this range of the envelope. With the new set, it was a little bit closer. There were a few more in that range, but again, a number of them were outside that sands and silty range. Here's that flooding test again. And here's the kinds of results that you get from the flood test. The thing that's interesting about this is that because they can monitor the subsurface groundwater elevation, they can, and this is a little bit outside my range of expertise, but this is what Jenny has explained, that they can discern the infiltration rate of the subgrade separate from the infiltration rate of the bioretention soil media. And in the design infiltration rate that was put in the TIR, these are the rates that the engineers put in, but then these are the rates that we actually measured in the field. So for you engineers and other hydrogeologists, this starts to get very conceptual below the ground, but you start to see that there's a little bit of consistency in some of them, but some of them are quite different. That's one of the main findings that we're seeing in the engineers' design reports compared to what we're seeing in the field. With the vegetation, you may have heard this before, but there's maybe historically in the last 10 or 15 years, there's been somewhat of a misconception amongst some landscape architects that somehow bioretention facilities are really wet. And there's a tendency to specify really wet plants. But Anne is telling us the cells were mostly planted with plants that grow in wet or wet conditions, when in fact the units are incredibly well draining. They should be planted with more dry tolerant plants that can tolerate brief inundations of water, but not if the unit is located on till. Of course, that caveat at the end is if a facility is located on till that doesn't drain quickly and it doesn't have an under drain, the water can sit there longer. But overall, these facilities are both very dry and they're associated with buildings and parking lots. And so in the summertime especially, they can get extremely hot and it's very stressful on the plants. In my discussions with some of the facility owners, it's clear that post-construction maintenance of these facilities is their biggest concern. They leave the design of the things to the engineers and the contractors to build it. But then once they move in, they own it, and they have a considerable challenge in maintaining the plant community based on how dry it gets. Never mind the maintenance staff that needs to do it. So for the vegetation, shrub species were surviving well, the herbaceous species less so because they depend on more irrigation. Their root system is shallower, so they need that near surface water. Selecting fewer, more successful species will lead to greater survival and reduced plant and maintenance costs. And there are recurring issues of plant die-off, invasive species replanting, and lack of maintenance staff capacity. One of the other interesting results that we observed, even more so in the second set, is that when the water flows into the facility, because the bioretention soil is so highly infiltrating, a lot of the infiltration happens before it ever progresses across the cell itself. So it's very uneven. And plants that are closer to the inflow will receive more water, and plants farther away will remain drier. This also could, actually in one of the other sites that we looked at in the first 10, it had a considerable effect on the infiltration of water through the bioretention soil media and getting to the underdrain quickly, which essentially caused like a bypassing of the distribution across all of the soil media. And as Doug was reminding me in the model is a one-dimensional model, which means that it assumes that as the water enters the facility, it immediately flows across the entire bottom of the facility and responds as an even pool across the whole facility, when after it's built, it's generally anything but that. With the modeling, the bioretention facility can meet both flow and water quality goals if designed correctly, but you can't design it if you can't model the hydrology correctly.
Bill, this is Jenny. Did you want to take questions as we go? There is one.
Yes, we said that at the beginning, and I've been trying to go a little bit slow to allow people to ask questions. Maybe now is a good time to open it up.
So Shanti has a question in the chat. She's
good. I don't see my chat.
I'll go ahead and read it. It's curious about the age of facilities in your table that showed infiltration rates. We have found that infiltration rates increase over time. So curious if the rates that are higher than design are older systems.
Do you want to answer that, Jenny?
I think that's a great question. The age of the facilities in our current study, they're only a couple of years old, but in the first set of 10, we did have a few much older systems. And in general, I don't think we have enough facilities to have a good correlation between age and infiltration rate. But we can say that all of the infiltration rates we measured exceed the long-term assumed performance rate. And Doug, correct me if I said that wrong.
Shanti, that's interesting that you suggest that infiltration rates increase over time, because part of the what's incorporated in the design process is something of an anticipation that in fact the infiltration rates will decrease over time.
And yeah, I know. I mean, that's why we have the safety factor. I think that in general, we haven't found that to be true. It probably has a lot to do with how you design your system and how much is going to it. You know, for the roadside bioretention type facilities, you're not generally getting that much of a load. I think the idea is that the plants and the roots are really helping to keep infiltration rates alive and well. And I think that's what we've found. Of course, we haven't done widespread monitoring of this, but of the facilities that we have, we've generally seen an increase in rates.
That's so interesting. And in fact, we have a follow-on proposal with the stormwater action monitoring that addresses this question specifically, that we're proposing to find quite a number of another set of facilities that are actually older, up to 15 plus years, and go out and not do any of the overall hydrologic continuous flow monitoring, but just do the infiltration tests on many, many more facilities and evaluate that specific question. And
yeah, that'd be great.
Yeah, it's I've been in our proposal, that we're suggesting to do 50 facilities.
Yeah, because in
not just
theory, if we're putting safety factors on all of these for degradation that's not happening, then we're way over designing them.
That is exactly the question. You're right on it.
Which then gets to what you're talking about with the plants not getting enough water.
Right, right. Never mind not getting enough contact time for any water quality treatment that you might be expecting if the water had flowed across the facility.
Right.
Yeah, thank you for that question. Any other questions on the hydrogeology or plants before we get into the modeling? Thanks for breaking the ice, Shanti.
Sure, happy to help.
Okay, oh, I see, interesting. Little detail on Zoom, if you have more than one screen, your scrolling mouse doesn't work unless your cursor is on the screen that you're wanting to scroll. So we're getting into Doug's work that he did, and everyone should know Doug. He's the author of the Western Washington hydrology model that's used through Department of Ecology. In the first set, I'm looking at this phase one site designs. In the first set, they did not have the benefit of the bioretention module. And so they have to essentially design a makeshift trench or some other kind of fake bioretention model in the model. And there were some other models entirely that were used for design, but they didn't have that multi-layer bioretention module that's presently available. The approach to modeling was often not set up properly. And for that first set of facilities, none of which were retrofits, the hydrologic performance of the facilities was more due to oversizing facilities for 100% infiltration, masking any design errors or incorrect assumptions. So essentially, there was very little observable response that we could see in the range where the facility would start to, for example, fill up considerably or even overflow. I don't believe we had any overflows in the first sets. So the oversizing essentially didn't allow for a lot of response in the facility to evaluate much. In the phase two site designs, using the WWHM 2012, and most of them using the bioretention module, one actually did not, even though it was available. Some models using the bioretention module did not have the model parameters input properly. And I put this asterisk here because we'll address that here in the next slide or two. And in this set of 10, the hydrologic performance of the facilities was mostly due to small size of some of the facilities or low set overflow elevations. So as you can imagine, in the one photo of the flood test where the overflow elevation was quite high and the contact area was quite large, some of them, mostly because of how small they were, maybe they were misinstalled, or if they were playing it safe to have a low elevation, but a couple of them only had an overflow of 2 inches or so above the bottom of the bioretention facility. And because of that, it would go into overflow quite easily. So here's for the engineers, we had a request after the first presentation of this in the North Sound permittees group that actually some of the engineers wished they had attended, and they wanted to know more about what the engineers need to be doing better to be more accurate in the modeling. Some of these are pretty obvious, but it just shows that for you permit application reviewers, these are some of the things that you really need to be looking for. That the construction plan should match the design documents, which should match the bioretention model inputs. These are just numeric consistency between the various design documents. The model drainage area and the bioretention areas should match the actual areas. So it's very important to know what your contributing drainage area is, because just to begin with, that's the source of your water. And if you don't have the source of your water right going into the rest of your system, everything else is who knows what it's going to do. So just the first steps of the inputs need to be accurate. The model native soil infiltration rate should match the geotechnical infiltration test rate. Another obvious consistency that needs to be met between what you're seeing in the field and what you're inputting into the model. And by the way, this goes back to Jenny's point to our team, is that often the geotechnical infiltration tests were not done where the cell was going to be built. And that in our area, the subsurface infiltration conditions can vary on very short distances within a site. So she's really emphasized that that testing needs to be done right where you're going to build the facility. The bioretention overflow structure inlet heights should allow for at least 6 inches of surface ponding. Again, this is to help spread any ponding over and actually have a contact area that's large enough to be meaningful in the infiltration. And the soil mix used for bioretention soil layer should match ecology's bioretention soil specifications. This goes back to that soil composition distribution with the guidelines envelope that's highlighted. In the summary of the model results, WWHM 2012 fairly accurately mimicked what was measured in the field. But Doug recommends adding a vegetative litter when there's going to be some finer material on the surface of the bioretention media, and also to increase evapotranspiration from the bioretention soil mix. So this is getting a little bit into the technical details of the model itself, but it's of interest to the engineers to help model it more accurately. Recommendations from the Bhp Phase Two. Again, maintain a bioretention top area, at least 5% of the drainage area. Maintain a minimum 6-inch riser height. Maintain a minimum of 18-inch bioretention soil mix and meet the size distribution criteria. And specify planting plan of plantings that reflects the relatively dry and well-drained conditions of bioretention facilities. So there is our presentation for today, and one of our facilities in the middle of summer with our crew actively collecting the data. So please reflect back on what we've got here and ask us some questions. Doug, you want to comment more on the model setup? We've been talking about that a little bit between the expected infiltration rates and how it's set up with your new bioretention module.
Sure. I think that, there's a lot of input involved with the modeling of a bioretention facility, and some of it's a bit confusing. So I think it's important that if you're the design engineer or even the reviewer looking at, what all this stuff means, there's a lot of documentation available in the WWHM 2012 user manual. So that's a good resource for people when they want to better understand exactly how this whole thing works with bioretention and how to properly set up the model. So that is certainly a good place to start. Also, if for some reason, you still have questions, you're always welcome to contact me, either by phone or by email, and say, look, I'm trying to figure out how to do this. What's the best way to approach it? And I'm happy to answer your questions.
Thank you. And I'm seeing a couple of questions. Chris Berg, will you have a successful plant list available? And you want to talk about that for a moment?
Yeah, I can talk about that. I'm going to say, unfortunately, we more developed an unsuccessful plant list in reviewing the facilities as opposed to what exactly works. It was easier to say what exactly isn't working. I know that shrubs tend to have a much better survival than a lot of the herbaceous vegetation. I realize shrubs sometimes can be big and cause sightline problems, so they're not a perfect fit for every bioretention unit, but they do tend to seem to have they did measure as having a greater survival compared to a lot of the herbaceous stuff. And then pretty much I would say, so there's a measurement used for plants when you're doing wetland work, and it's called a wetland indicator status. So your herbaceous plants, you want to tend towards kind of on the drier side, maybe a facultative or a facultative upland rating on the wetland indicator status, as opposed to many of the plants have an obligate rating that are installed in these facilities. An obligate rating means essentially they occur 99% of the time in wetlands. So you want to trend towards, I guess, more of a plant that would only occur maybe 50% of the time in wetlands, which would be a facultative plant. So I'm hoping that's I hope that answered your question.
A couple other things that I've heard you talk about before is that, and I've heard from the owners, is that some of the more esoteric plants are hard to obtain, never mind whether they'll survive or not. And there has been some of the local jurisdictions that take the planting plan as, as a contract document that those are the plants that have to be met. And if they start to die, it's hard to find some of those more unusual plants, never mind if they died the first time, it's likely they're going to die the second time. So simplifying, what I'm hearing you say, Anne, is simplifying quite a lot can help for the long-term success rate.
I don't know if it's simplified. I don't think we need to put exotics or hard to find plants in these facilities. As I said, it's kind of maybe putting plants around the inflow or the inlet that like more wet conditions, and then plant kind of in a fan out towards more drier conditions. And that'll actually give you, I think, better success, and also possibly as the facilities age and things may or may not change, which I've always assumed they would get more wet, but it sounds like maybe they aren't, that the wet plants would still be around and could seed and become more prolific, or if the plant facilities are more dry, that the dry plants seed and become more prolific.
Oh, that's right. Good. Let's see, next question. Hi, Dawn, I see your question here. Did you look at how maintenance practices affect the function of the facility? And yes, we did. And I looked at that. And actually in our next proposal, that's going to be a big part of much more rigorous part of our documentation of these older facilities that we're proposing to look at for their infiltration rates once they become older. But a little bit more anecdotally, I spoke with quite a number of the school district maintenance staff, and they very much want to not have to weed. And when there is weeding, there can be an effect of compaction. So it's can be counterproductive. They're also very resistant to replanting if they don't have to. There were a couple of them that said, why can't we just plant grass and mow it? And so the plant composition, not only for maintenance of infiltration, as Shanti was suggesting, might be happening, but just for acceptance by the institution, seems to be really important for the long-term success of these facilities. Did you have a follow-up, any detailed question you had on that, Don?
No, thank you for answering that, Bill. I was just curious if you'd looked at it. Some of our older facilities, I've just been wondering how well they're operating based on our maintenance practices.
Actually, in the first set, you're over in Bellevue, right?
Yeah, correct.
So in our first set of facilities, we studied the long facility along, what is it, 145th?
Yeah, north of the college there.
Yes, and that was an example in the first set where infiltration was happening mostly at the upstream end of that. It had relatively long, it was relatively long and relatively steeply sloped. And as I recall, there was quite a lot of infiltration at the upper end before it even reached the lower end. Is that right, Brian? Do you remember that?
I'll jump in, Bill. That is right. We ended up running 2 infiltration tests in that one just to get saturation across the entire facility. The other observation I wanted to make about maintenance was the difference between narrow facilities and more round or square facilities. We did notice, I guess, an edge compaction effect for the narrow facilities. And I don't think we had a high enough sample size to correlate it to, degree of maintenance. But at the edges of the narrower facilities did have compaction along the margins relative to the center. And I think it affected the infiltration rates across that surface.
So are you suggesting that maybe maintenance access or just local pedestrian access might contribute to that edge compaction?
We saw it in the narrow facilities and we didn't see it in the wide ones. So any walking adjacent to or within the facility is going to have a larger effect on a narrower facility, I think. What we saw.
Okay. Next question from Susan McCleary. Many of our jurisdictions offer incentives for residential rain garden implementation. We are using a rain garden handbook for Western Washington as a guide for installation. Any idea if this research will be used to amend the handbook? I'm referring mostly to the information regarding plants. Well, that's good. A question of transfer of knowledge gained to another program. I don't know about that. Yeah, I really don't know, but it would seem that it would be worthwhile to do that and give the residential users a little variety or maybe better success with the plants that they choose.
Bill,
And, yes.
you missed a question from Rachel.
Oh.
Right behind Dawn's.
Oh, I'm sorry. Pardon me,
Just
Rachel.
FYI.
I'm sorry. Thank you for catching that. I should probably maximize this screen of the questions. From Rachel, did some of the facilities selected have under drains? If so, did any recommendations arise that are specific to those facilities? Let me go back real fast to a table. this table. Okay, this table, I added an indicator after the site names for R retrofit or U underdrained. So you can see that some of them were in fact underdrained. Not all of them were both. So yes, they were. And were there any recommendations that are arising from that? Doug and Jenny, what are your thoughts on that?
Well, I think one of the problems that you can have with an underdrain system is that if the inlet and the outlet are fairly close together, you can basically short circuit your whole bioretention system, and the underdrain basically then just takes all the water and dumps it out into your municipal storm sewer system. So I think it's critical that you place the underdrain in the appropriate place, and that the discharge from it can be basically regulated by putting in some sort of control on that underdrain, so that you can basically govern the amount of water that you're releasing. So there are some constraints and some issues with underdrains that you just need to take into account if you're going to use one. Now, if you can't infiltrate into the native soil, you have to have an underdrain because the water has to go somewhere. So oftentimes, that's the reason why they're included in the design.
And there's not enough lateral flow on till native soil for it to flow away laterally.
Well, you don't necessarily want it to just do that and go anywhere. That's oftentimes how you end up with water in people's basements.
It's going somewhere else.
It's a good idea to make sure that you know where that water is going to go.
Best to go straight down one way or the other, or to an underdrain.
Exactly.
Jenny, any thoughts?
Whether you control the underdrain with an orifice, or you have a bioretention soil that's not so quickly draining, it's a little bit of chicken and egg. And so the reason underdrain facilities may not do great at the flow control is because water readily soaks through that bioretention soil, and it doesn't contain the water in the way that the model thinks it does. Because as Shanti pointed out, some of that bioretention soil has initial infiltration rates of 100 plus inches per hour, but the model is showing it at a much lower rate, tied back to an assumed decline over the life of the facility. So initially, underdrain systems drain the water very quickly to the pipe that then discharges it to whether it's a pond or the storm system. And so
Right.
I think the question was about recommendations specific to underdrain versus infiltrating. And what we saw was plant communities in underdrain systems were water stressed. In systems that were not underdrained, the rates were lower. Still good infiltration rates, but not, let's say, that.
Can you restate that last part again?
Underdrain systems, the plants were more water stressed. They were very dry. And infiltrating bioretention, the infiltration rates were not as rapid, and so less stress.
That's a good connection between the underdrain systems and the plant community. Okay, I want to make sure we get all these. Clay, hi Clay. Wetland indicator status should not be misused or misconstrued as an assessment of how wet or how deep a species will tolerate. Sluice sedge, Carex obnupta, is a great example of how this misuse can be misled. And I think Anne has some observations on Carex obnupta from our projects.
Yeah, I mean, sluice sedge was actually one of the few obligate plants that did really well in the rain gardens or bioretention cells. And that was kind of like an exception to the rule, I guess.
Clay, is there any follow-up or kind of other angle on that you want to add?
No, I was just making the point that wetland indicator status was developed for a very specific reason and really shouldn't be used to guide these kinds of plant selection decisions. I think the bottom line is that we need a lot more investigation as to what plants do survive in these facilities. And that's conducted through experimentation, just trying different things, a real critical look at what is known about plants and their tolerances of these kinds of flashy hydrologic situations.
Right, that's a good description of it. Flashy, and then seasonally extreme. Okay, Lori, I see we're coming up to the end of our hour. And if anyone wants to do that, but otherwise,